So most of us are familiar with this kind of figure, which illustrates the summer solstice, winter solstice, solstices, and the equinoxes. The equinoxes will be here on the line perpendicular to this line, this axis, uh, coinciding with the sun. So we haven't shown the equinoctial points. So this is the summer solstice. What this is summer, northern summer, but southern winter. So most of the definition are with respect to the northern hemisphere, biased towards the northern hemisphere. So here, this is the equator. We see that sun is located above the equator in the northern hemisphere, directly over the northern hemisphere. And in this location, in this configuration, the sun is located below the equator, directly over the southern hemisphere. So this is the southern summer. This is the northern summer. So this is the summer, and this is the spin axis. So the earth will be rotating around like this, and this is the uh, axis which denotes the angular velocity, and this is the equator. This white line is the equator. So and this is the spin axis. So what we can so we'll consider a component of the spin axis on the ecliptic plane. So basically this spin axis will have two components, one perpendicular to the ecliptic plane and the another which is in the ecliptic plane. So it may be pointing towards the sun in this summer solstice because the tilt is towards the sun, or it can be pointing away from the sun, this blue line, this blue vector, which is the component of the spin on the ecliptic plane. It can be away, or in the equinox points it will be perpendicular to the position vector originating from the sun. So if there is a line from here which is coming and joining here perpendicularly, perpendicular to this line, this will be the equinox point, and this will be oriented perpendicular to this line. So like this. So these are all the orientation of the this spin axis, component of the spin axis on the ecliptic plane. So this is at the equinox. So this will be, so if the earth is revolving like this will be the autumnal equinox. So if we join this line from here, from the center of the sun to the center of the earth will be here. This line will be perpendicular to this, and these are the other places. So if the earth is here, the component will be directed like this. If the earth is here, the component will be directed like this. So overall, in an ideal case, what we expect is this thing doesn't change its orientation. The spin rate remains the same, and also the tilt also remains the same. There is no precession, that is, the spin axis does not oscillate or does not go around in a circle and such. So all this remain parallel to each other, and the spin axis here remains parallel to the spin axis here. And also we expect that the shape of this ellipse does not change. This is the elliptical orbit, or neither the orientation of the elliptical orbit. It does not itself rotate in a circle or something like that. So that is, in the ideal case, that's what we expect. But in reality, that is not true. Both this ellipse, the elliptical orbit itself is rotating, and this spin axis is also rotating or precessing in a circle, and so on. So if nothing is changing, if we define that the earth starts from here, completes one cycle and returns back to the same position, then whether we define this as whether the sun starts from the largest distance from the whether the earth starts from the largest distance from the sun, which is called the perihelion. So this distance is the largest, this is the smallest distance. So if earth starts from the perihelion and comes back to the perihelion, it will be at the same point. Or if we consider that the orientation of this component of the spin axis should be the same. So right now it is directed towards the sun. So after completing one cycle, it should be directed towards the sun. So in this case, in the ideal case where nothing, all this the shape and the spin axis and all remain constant, either we define as the perihelion to perihelion period, or we define the spin axis period, that the spin axis comes back to the same orientation at the beginning, or we define this revolution with respect to some distant stars, all the zodiac signs, the Aries, Taurus and all. any of them will give the same result. They will have the same periodicity when these things are changed. When the ellipse is the same, it's the shape and the orientation is the same, and the spin axis is the same, remains constant, the rate remains constant, and the directions, the orientation remains constant. All three, there are a couple of definitions that we can use for defining an year, and all those definitions match in the ideal case, because all these things are not changing. But in reality, all these things change. They have minute, if not some major variation, at least some minor variation is there. So let's define, let's see what is the some of those definitions. So the first we will see, look at it, this anomalistic year. So anomalistic year is defined as the period from perihelion to perihelion. So Earth starts from the perihelion, that is the greatest distance from the sun, and it comes back to the same point as in perihelion, the greatest distance from the sun. So if there is no precession, if this ellipse itself is not rotating or precessing, then this will be the same point it will be back to. But in reality, in the Earth Sun configuration, this ellipse, whatever this black ellipse, it is slowly precessing. It is slowly rotating in the same direction where the Earth is revolving. So if this is the direction of the Earth's revolution, this axis is also rotating in this direction. So it starts from here and goes. So initially it was here, now it's in this direction, oriented in this direction. So the sun starts from here, the Earth starts from here, it goes around and then slowly shifts to this green orbit, green path, and then comes back. So by the time the Earth comes back to its original kind of location, the ellipse would have shifted by some amount. So in order to, or it could have shifted on the other side, but in our case it would have shifted on this direction, on the same sense as the direction of rotation. So when it comes back, this ellipse, the perihelion point would have moved further away, so the Earth has to move further in order to catch up with the perihelion point. So this will be the next perihelion. It starts from here, goes and comes back to a different point, but this is still the greatest distance, so because the whole ellipse itself has rotated. So this is called the anomalistic year, perihelion to perihelion, and it has a period of 365.2596 days. Next we'll look at the sidereal year. So it has a period of 365.2564 days, which is slightly less than the anomalistic year. So the sidereal is defined as with respect to the background stars. So this red line connecting the Earth, the Sun, and this distant star, some nakshatra or some zodiac sign, these 3 points should be collinear. They have to be on this straight line. That is the definition. So when the Earth completes one revolution and comes back, it has to come back on top of on this line only. So in the final position, also the 3 points should be collinear. So the final position of the Earth, the Sun, and the star should also be same on this line. I mean, they should be collinear like in the initial condition. So if it starts at 0 degree Aries, the relative position of the Sun as seen from Earth. So initially, if we see that the Sun is at 0 degree Aries, so after completion of one whole revolution, also the Sun should come back to 0 degree Aries as seen from Earth. So suppose, so if the ellipse is precessing, so it will not come back to the exact this position, so it will be either closer to the Sun like this. Here if it comes back to this position, it will be closer to the Sun, or it can be further away from the Sun, but it should be on this line. In order to complete this whole cycle according to this definition based on this distant star, it has to be it has to come back on top of this line. It has to be collinear. This final position, the Sun and the star, has to be one same straight line that was in the beginning. So here also, here we don't consider the orientation of this component of the spin axis. Here also we don't consider the orientation of the spin axis. As long as it is back to the perihelion point, which is the greatest distance, we consider the cycle is complete. Here, as long as it is back onto this straight line, we consider the cycle is complete. We don't really care what is the direction of this component of the spin axis. So this is the sidereal year defined with respect to the distant stars. So another is the tropical year. So it has a period of 365.2422 days, which is slightly less than this. So this anomalistic year is slightly greater than the sidereal year, which is defined with respect to the stars. And the tropical year is basically defined with respect to the orientation of this component of the spin axis. We usually define it from equinox to equinox. So here the illustration is from say this one, summer solstice to summer solstice. So initially this direction, this was summer solstice, so the tilt was towards the sun. So this arrow, the component of the spin axis, is directed towards the sun. So when the whole revolution is complete, even in the final position, it should be directed towards the sun. This component of the spin axis should be directed towards the sun, and then we consider the cycle is complete. So we can see that this was the orientation at the initial position, and this is the final position, that there is a slight rotation of this spin axis, or the component of the spin axis, so that even in a different position it is getting aligned in this direction, so it's pointing towards the sun. So since this is the direction of the Earth's rotation, Earth's revolution, and the direction of the spin axis rotation is opposite to it, it reaches earlier. So this period will be slightly lower than this, because the direction of rotation is opposite to the direction of revolution. And here it is slightly more, because the direction of revolution of the Earth is in the same sense as this direction of this precession of the ellipse. So this is also called, this one is called apsidal precession, because this is called the apsis, this line, and this is rotating, so this is called the apsidal precession. And here this is, as we looked into the previous picture, this is due to the precession of the spin axis. So this is from equinox to equinox. This we have shown from solstice to solstice. So this is a summer solstice. So because it is slightly rotated at this position, again this will be solstice. It doesn't have to come back to this position and all, because since this rotation is there, it is directed towards the sun at this position only. So this is the next summer solstice. This was the summer solstice in the beginning. After one revolution, this will be the new summer solstice position. So it has shifted from this sidereal definition, or even from this perihelion to perihelion definition. So these three are completely different definitions. So if nothing changed, if it was all ideal, all three definitions will coincide and give the same period. But since the ellipse is precessing, the spin axis is precessing, and all, will get different definition, different time periods. So here this is the winter solstice. So this position, ideally it should have been exactly opposite to this on this line, but since the spin axis has rotated a bit, now it at this position only it is pointing directly away from the sun. So like this. So this was the winter solstice. The tilt was away from the sun. This component was directed away from the sun. So here this component is directly directed away from the sun here. So this is winter solstice. So ideally, if we want to look at the equinox to equinox, so this will be the equinox position. So if this is the perpendicular line to this apsis, these will be the two, there will be the autumnal equinox here and the spring equinox point here. So if this was the initial point and this was the orientation, so if this is the position vector joining the Earth to the Sun, this component of the spin axis will be perpendicular to this position vector. So even after one whole rotation, we expect that it should be perpendicular to the this position vector. This spin axis, the component of the spin axis, should be perpendicular to this position vector. Since this has rotated a bit, if there was no rotation, it will go through one whole revolution, the Earth, and it will come back to this position like this. All this will be parallel, there will be no change. But here there is slight rotation in this direction. The spin axis is precessing, so it will reach this point where it is perpendicular to the position vector a little earlier. So so this will be one spring equinox. After one whole revolution, this will be the another spring equinox. So these are the definitions of the anomalistic, sidereal, and the tropical years. Further, we'll see a new definition used by very ancient people, or the in very ancient times, moon was used because observing the sun, the background of the sun, what is the star system behind the sun, and all those would be difficult to observe. But moon and the stars and the zodiac and the nakshatras, the lunar mansions, are much easier to observe throughout the night, day in and day out. We can do a long term observation. So most of the earlier time definitions was mostly based on moon and the stars. So we'll look at it in the next slide.